Hello, we are looking at lesson 3.2 for Algebra 2. Welcome, thank you for watching. We are going to continue factoring and solving equations, except instead of it being quadratic equations, it might be cubic or quartic, meaning that we now have x cubed in our equation or x to the fourth in our equation. So that's what we're looking at today. It's no longer simply x squared. It could be x cubed or x to the fourth or whichever, right? So when we were factoring in the previous unit, which, by the way, if you have a question on factoring or need to see more or want to see the very beginnings of factoring, something that I said that would show up time and time again, if you need to see that, again, go back to Unit 2, Lesson 2 video, okay? Go back to that one. So greatest common factor. What is a greatest common factor? We've mentioned this before in the past. We're going to write it down again. It's the largest value and variable power that divides evenly into all terms of a polynomial. It's the largest valuable and variable power that divides evenly into all terms of a polynomial. So we've already talked about this before, but let's see it in action quickly here in these three examples. Let's first focus on the number. What's the largest number that evenly divides 35, 28, and 7? Hopefully the number that leaps to your head is 7. So I can factor out a 7 from all of these. All right. However, what else do all of these terms share? They share an x. So that's what we're getting at when it says variable power, variable referring to the x. What's the largest amount of x's that they share? We can pull an x out of each one. So 7x can be factored out, and we're left with negative 5x squared plus 4x plus 1. You see, when we factored out the x, these all lost 1. All right, because we factored it out. So the GCF is 7x. That is the GCF of that expression. All right, let's focus on the numbers again. What is the largest number that divides evenly into 72, 15, and 9? Well, I like to look at the smallest number and go, what is it divisible by? It's divisible by 1, 3, and 9. Right? Because it really comes down to the smallest number, not the biggest one, right? 72 is divisible by a lot, right? It's divisible by a ton of numbers. 9, not so much. It's only divisible by 1, 3, and 9. So all of these terms, are they divisible by 9? 72 is, but not 15. Are they all divisible by 3? Yes. When you factor out a 3, you're left with 24x to the 9th plus 5x to the 6th plus 3x cubed. So we found the biggest number, but what about these x's? Well, this has 9, 6, and 3. What's the largest variable power? X to the third. They all have at least 3 x's, so 3x to the third. I can yank that out, and we're left with 24x to the 6th, right? Because if I took 3 out, right, and there were 9, now there's only 6, plus 5x to the third. If there were 6, and I took 3 out, well, now there's 3, and I took all of them out of that one. So my GCF is 3x cubed. Let's do it again one more time. What's the largest number that divides each of these, well, that one's pretty easy. It's 2. X to the third minus 2x squared plus 2x minus 8. Do they share any x's? This guy doesn't have any. Yeah, these all have x's, but this one doesn't have any. It has to divide all terms. So really, the only thing that you can yank out of that is a 2. Sadly, that's all we can do. The GCF of that is 2. So why is that so important? Why are we dealing with that? Well, when it comes to factoring, and when it comes to factoring polynomials, and when I say polynomials, I'm now referring to stuff that has like a ton more x's in it, right? We're used to things that have looked like this. Time and time again, we're used to things that look like this. Now all of a sudden we have x cubed, x to the fourth, x to the fifth, and we don't like that, right? And there's not some like new way of factoring that we now have to learn, right? What we do is we try our hardest to get rid of the x's, so to speak, by finding a GCF. The first thing you do on every single one of these problems find a GCF. Sometimes that's all you can do. Sometimes you find the GCF and you're basically done, right? So let's put that to the test. What's the GCF of these two terms? Well, they're both even, so we can pull out a 2, and they both have x squared. So when I take the 2 out, when I take 2x squared out, I'm just left with an x. And there I'm left with minus 3. If you're at all wondering, how did he just get to that so quickly? Well, 2 divided by 2 is 1. And when I take x squared out, I'm left with only 1x. Negative 6 divided by 2 is negative 3. And when I take x squared out, well, it's gone. Also, another way to look at this is you should be able to put this back together. Is 2x squared times x going to give you 2x cubed? Yes, it is. Is 2x squared times negative 3 going to give you negative 6x squared? Yes, it is, right? I ripped it apart. We should be able to put it back together if need be. But I don't need to. I'm done, right? Actually, right? This ought to look familiar, right? This is a factor, right? This thing in a parenthesis like that, right? What do I do with my factors? I set my factors equal to 0. And like I said, if you do not remember me doing this on repeat for several lessons, I encourage you to go back and look at the Unit 2, Lesson 2 video, I believe is where it started, right? I think the first lesson was graphing. The second lesson was starting to solve. So I encourage you to go look at that if that's feeling a bit, if you're like, I don't know if I remember doing that, right? So we set our factors equal to 0, add the 3 over, x equals 3. Now you might be wondering, well, what about this? This looks kind of different and strange. Well, if you think about it, right, I can just set this equal to 0. That's something that I can solve, right? I'm just trying to get to a point where I can solve it, right? And by solve, I mean I need to be in a spot where I can set it equal to 0 and actually get an answer, right? This is set equal to 0, and I look at that and I'm like, what can I do? But when I break it up into two pieces, and maybe putting it in parentheses will help you. When I break it up into two pieces like this, I can set one factor equal to 0 and find a solution, and another factor equal to 0 and find a solution. And I'm like, oh, okay, there are my two solutions. 3 and 0. Let's do it again. I look at this and I'm like, that's ugly. There's too much going on. I can't just single-handedly solve that, right? So I need to break this up into smaller fragments. Those fragments are called factors. So what is the GCF? That's the first thing you look for. They don't share any numbers, right? That guy doesn't have a coefficient in front of it. So I guess it all comes down to the x's. I can pull out x cubed from each of these. If I take 3 away, how many am I left with? 2. And when I take all 3 away, what am I left with? 100. Now, I can set these factors equal to 0. X cubed equals 0, and x squared minus 100 equals 0. How do I know that I can set them equal to 0? And how do I know I don't need to keep going? Well, part of it, I gotta be honest, is intuition. I just kind of know. I've solved so many. But this is a problem that we've seen several times. Can I get the squared thing on its own? Do you remember me saying that several times? If I can get the squared thing on its own, like I have just here, and then take the square root, oh, voila, I'm getting a couple of solutions, right? I look at this and go, oh, I can solve that. If I set it equal to 0, I know how to approach that, right? I don't look at that and go, well, I'm not even sure what's going to happen there. I look at that and realize, oh, I can get the squared thing on its own, so let's do that. And when I look at this, well, you might not look at that and realize anything, but what cubed equals 0? Right? Don't overthink it. What number cubed would equal 0? 2 cubed equals 8. 3 cubed equals 27. Only 0 would work here, right? 0 times 0 times 0 is always going to give you 0. There's no other way to get 0 in that situation. So that was just a bit of logic, all right? And if you will, just a little bit of logic there that 0 is the only thing that makes sense in that situation, right? 0 times 0 times 0 is going to give me 0. All right, let's keep it going. The more we do this, the more we'll get a hang of it. Always look for the GCF first. What is the GCF of these numbers, right? If we just look at the numbers, they're all divisible by, maybe you see it, maybe you don't, but break out a calculator and double check, right? I look at this, the smallest number, and I'm like, it's divisible by 1 or 3. So if these numbers are only divisible by 1, then who cares? But if they're divisible by 3, that's something we like, and they are, in fact, divisible by 3. We can yank a 3 out, but also they all share at least one x. So boom. So when I yank that out, take the 3 out, it's gone. Take an x from x cubed, I'm left with x squared. Plus 15 divided by 3 is 5. Take an x from x squared, I'm only left with 1x. And then take a 3 from 72, I'm left with, if you don't know, bust out a calculator, but it's 24. And when I take an x away from x, it's just gone completely. So I've factored it. I can set this guy equal to 0 and solve. And I get 0, of course. But what happens when I set this guy equal to 0? Right? I've factored it up, but I didn't factor it all the way. When I get here, I'm like, well, that just looks like another problem. Well, what? Yes, in fact, it is. It's a factoring problem. This is something we've seen many a time, right? Some of you have been using Desmos to solve stuff like this. I'm doing it all by hand. I'm factoring everything by hand here. And this is where I come in and use my U method once again. So negative b, or b over 2 minus u times b over 2 plus u equals c. So 5 over 2 minus u, 5 over 2 plus u equals negative 24. So 25 fourths minus u squared equals negative 24. Add the u squared over, add the 24 over. I'm going to turn that into 4 over 4. That becomes 25 fourths plus 96 fourths. equals u squared. 25 plus 96 is 121 over 4 equals u squared. I can take the square root of that, and I get 11 over 2 equals u. I know. Some of us don't like fractions, but the more you do this, the easier it's going to seem, right? And the more steps you can skip, right? The more steps you can skip. So I get 11 halves equals u. So 5 halves plus 11 halves, 5 halves minus 11 halves, I get 8. And 5 minus 11 is what? Negative 6, so negative 3. Remember, those are my factors. So what did I do all that work for, right? What did I do all that work for? Well, that means that this expression from the original problem factors into x plus 8, x minus 3. So my three solutions are 0, negative 8, and 3. Let's do it again because the same problem does the same thing. And I'll compare and contrast. So if there was some, you can obviously go back and rewind. You're watching a video right now, but let me compare and contrast the two. So what was the first thing we did? Let's do what we know how to do. Find the GCF. And something that I'm just now noticing in this problem, it's not set equal to 0. So let's set it equal to 0 first, which is annoying, but we'll do it. All right, so I subtracted that over. Notice I put it in the middle, so that way it was in standard form, right? 8, 7, 6. Okay, now let's find the GCF. That's what I did over here with 3x. I look at these, and I go, they're all even numbers, so I know they're all divisible by 2, and then there's lots of x's hanging around, so let's deal with that. Our GCF is 2, and they all have 6 x's, so x to the 6th. So the 2's gone, and I'm left with x squared. Negative 26 divided by 2 is negative 13. Take 6 of the x's away, I'm left with 1. Take all the x's away and divide 72 by 2, you get 36. So we're at this stage here. Take out the GCF, right? Remember, in my factoring video, I said that, and some of you will get good at this in your head, right? When I look at this expression, so this is a throwback to the factoring video, so I'll hit on this for like 2 seconds. I'm looking for two numbers that do the following. Multiply to negative 24 and add to 5. That's what these two numbers are. 8 times negative 3 is negative 24. And 8 plus negative 3 is positive 5. I need two numbers that multiply to the last number and add to the middle. So I look at this. What are two numbers that multiply to 36 and add to negative 13? If you know the answer to that, great. If not, then you need to have some sort of method of getting there. And I'm trying to reduce the amount of guessing and increase the amount of solving. So you can sit here and guess two numbers that multiply to 36 and add to negative 13, and you might know the answer. That's totally fine. But my U method is just a way of getting there without having to guess. Okay? So negative 13 over 2 minus U times negative 13 over 2 plus U equals 36. So I end up with 169 fourths minus U squared equals 36. Add the U squared over, subtract the 36. get a common denominator by multiplying by 4 over 4. You can't see my calculator, but I'm doing 36 times 4, and I get 144. So 169 over 4 minus 144 over 4 equals u squared. 169 minus 144 is 25/4, which equals u squared. Take the square root, and you get 5/2. So again, what does this mean? You plug it into these guys up here. Negative 13/2 plus 5/2, negative 13/2 minus 5/2. You get negative 13 plus 5 is negative 8 divided by 2 is negative 4. And negative 13 minus 5 is negative 18 divided by 2 is negative 9. Did you guess those two numbers at the beginning? Negative 9 times negative 4 is positive 36. And negative 9 plus negative 4 is negative 13. So before I end up finishing here, right, compare and contrast. We pulled out the GCF, but then we get to this and realize, wait a minute, I can't just set that equal to 0 and solve like some of these other easier ones, right? I have to factor it and solve it like all the other problems from Unit 2, right? This has just become a problem from Unit 2. That's literally all that is, right? And I'm not joking, and I'm not being facetious. I'm not kidding, and I'm looking you dead in the eyes and going, it's literally the same thing as Unit 2. And if you think it's any different, you're overwhelmed. You're thinking about it too hard. It's literally the exact same thing we were doing from Unit 2. So whatever you feel comfortable doing from Unit 2, whether it was completing the square, whether it was my U method that I'm doing right here, whether, it's up to you, right? But somehow you have to get to this point where, okay, I can factor out 2x to the 6th, and now I know that this breaks up into x minus 4 times x minus 9. And now I can see my 3 solutions. This one is 0, this one is 4, and this one is 9. Okay. So, there's this other little thing here where sometimes we end up with an expression that looks kind of interesting, where it skips the cube term and skips the x term. And the comparison that we're trying to make here with this is an expression in the form blah is in quadratic form. You see the comparison we're trying to make here? Look at this. Look at these two expressions, right? They're eerily similar, right? But this one has x to the 4th and x squared, where this one has x squared and x. This guy factors up into this. We know that, okay? We've seen that time and time again, how something like this factors into this, right? 7 times 2 is 14, and 7 plus 2 is 9. Well, we're looking at this and going, well, it kind of fits that pattern, except instead of 2 and 1, I have 4 and 2. It's like the same thing, but yet it's not. And the one difference is that when it factors into something that looks like this, right? So instead of x plus 7, it's x squared plus 7. Instead of x plus 2, it's x squared plus 2. Okay? So think of this problem compared to this problem, right? They practically have the same form, except it's just off by a little bit, right? And this is different from these guys up here, right? This was cubed and 8 and all kinds of different things were happening, right? This is like following the exact same pattern where it's got, so this thing squared gives you x squared. Well, x squared squared gives you x to the fourth. And oh, this is a constant. It's like fitting the pattern almost the exact same way. I don't know if I'm dwelling on that too much, but I just need us to realize that the pattern's the same. So if I were to solve this guy, well, again, I'm going to use my U method for the sake of consistency. So negative 10 divided by 2, well, I'm just going to write that as 5. Plus U, negative 5. Minus U equals 9. So 25 minus U squared equals 9. Subtract the 9, you get 16. Add the U squared, you get U squared. Take the square root. U equals 4. So my two numbers are negative 5 plus 4, negative 5 minus 4. And I get negative 1 and negative 9. Remember, we just need two numbers that multiply to 9 and add to negative 10. That's what these two numbers do. Negative 9 times negative 1 is positive 9. And negative 1 times plus negative 9 is negative 10. So that means that this factors into x minus 1, x minus 9. Okay. Well, if that's what this factors into, then this is going to do the exact same thing, except it's going to be x squared. Now, what can we do with these guys? Set them equal to 0 and solve. So where this one has only 2 solutions, this one has 1, 2, 3, 4 solutions. All right, let's do it again. I look at this problem and I'm essentially pretending for a few moments that, oh, let's just imagine that this is a 2 and this is a 1, right? And I'll just write it out like I did over here, right? You don't need to write this out every time. But I'm just imagining that this is true instead, okay? So I'm going to pretend to solve that for a second. B over 2, B is 1, negative 1. Boom. 7/2 equals U. I didn't say anything while I was solving that. I kind of got in the zone. But this times this gives me the 1/4. And I added the U squared over, added the 12 over, got a common denominator, added. All right. I don't know. I've done it like 4 times now. So I just feel like, if anything, just go back and hear me say the same thing on the other ones. So 7/2 equals U. So negative 1/2 minus 7/2. Where am I getting this from? From the tippy top. So that gets me negative 8/2, which is negative 4. And then negative halves plus 7/2, which gives me 6/2, which is 3. Again, what are two numbers that multiply to negative 12 and add to negative 1? What are two numbers that multiply to negative 12 and add to negative 1? Negative 4 times 3 is negative 12, and negative 4 plus 3 is negative 1. So this thing factors into x minus 4, x plus 3, which means this thing factors into x squared minus 4, x squared plus 3. Set your factors equal to 0. And again, how do I know that I shouldn't keep going? How do I know that I can just, because like up here I was like, well, we factored out the GCF, but I got to keep going. Here I factor it once and I'm like, well, let's set them equal to 0. I just realized that when I do this, I can get the squared thing on its own and perform a solve like this, right? I just look at that and know that, right? I look at that and go, well, I can easily just move the 4 over and take the square root. I can just imagine where the problem's going to go. And when I do that to this guy, what's going to happen here? We have our first imaginary solution. All right, so this is a mixture of, or this is more of the same thing happening over and over. Okay, that's what this is. More of the same thing happening over and over down here. So I don't know if it benefits you to see a million more examples or if it's just something that maybe you can just rewatch, but I figure I could at least show you what it will eventually factor into and give you your solutions. Okay. If you want to do these on your own time and you want to talk to me, if you still were kind of confused, you can totally let me know. It's my birthday today and my dad's calling me. I'm gonna pick it up and I'm gonna end it right here. All right. Hello?